Are we live already? Looks like we're live. Hello everyone and welcome, excuse me, to yet another Zoozing session. How about that? Let's make a little announcement. Super quick. Red circle live on Twitch. And what are we doing today on Twitch? Today we're implementing anti-aliasing, aliasing in C. I'm gonna give the link to the Twitch channel where we're doing all of that, and I'm gonna ping everyone who's interested in being pinged, and there we go. The stream has been officially started. How about that? I bet you expect that shit to happen as usual. So today we're gonna continue developing Olive.c, which is the C library that we've been developing for several streams already, I think, and it's basically a simple graphics library that renders everything into memory, right? So it does all of that on CPU, and it renders everything into a region of pixels that you allocate it in memory yourself, and it doesn't depend on any third-party libraries, right? So it's basically self-contained single file that knows how to render different primitives in memory that you can use then to generate images, maybe generate animations, videos, or maybe like make some games or something like that. It's a very simple thing that is self-contained. You can find it in here, right? So I'm gonna copy paste it in the chat. And for people who's watching on YouTube, if I ever upload that to YouTube, I'm going to put that in the description as well. So I'm gonna have references. Right, so, and I need to copy paste this link in here. There we go. So this should be in the description now, hopefully one day. So let's take a look at what we have. All right. So this library, as I already said, it is pretty straightforward, right? So I would like to take a look at some example maybe. Right, usually there is this following sort of structure. I probably need to actually move this example away into separate file because I want to have like a syntax highlighting for this thing. So let me quickly do that. CMC, well, there we go. So usually what you do, you allocate array of pixels. A single pixel is 32-bit integer, unsigned integer. Right, you allocate enough pixels for your width and height. And then you essentially create a canvas out of that pixels, right? And then you can fill something with it, like you can fill every pixel with the white color, and then you can render a circle at a particular position, and it will actually render that in the pixels themselves, like in here, right? And then using libraries like STB, you can actually save all of that stuff on the hard drive. Right, so let's actually save this program and see how it works. So this particular program generates a flag of Japan, right? So let's actually see if it's going to work. I'm going to save that to flag.gp.c, right? And I'm going to just compile it, flag.gp.c. So let me see. Okay, so it requires the STB. As far as I know, STB is located in third-party folder, right? So that should be available. There you go. Right, so we have executable flag.gp, and if I run this entire thing, it should generate flag.gp.png. And if I open it, it looks like a flag of Japan. Right, so, and we generated that using our library, right? Essentially, as I already said, we filled all of the pixels with white color, and then at the center of the canvas, we filled like a red circle, right? So that's essentially what we did. A pretty straightforward thing. So you can actually do different primitives, not only circles. You can do rectangles, right? So I have a list of the different primitives that you can do right now. Right, so you can do rectangles, circles, lines, triangles. In the future, I plan to add ellipses and stuff like that. Maybe some sort of like curves, like Bezier curves. Who knows? Maybe I should actually put it to do that. Right, Bezier curves. Right, that sounds like a good idea. Right, essentially, this library becomes like a collection of everything I know about geometry. Right. Essentially, I think. So that basically I've been doing different things related to graphics and geometry and decided one day to systemize my knowledge about all of that. And I guess this library is going to be basically systematization of all of the knowledge that I have about computer graphics, which is not that bad of an idea, actually. I think that's pretty cool. Because every time I learn something new, I can just extend this library, right? So yeah, that's pretty cool. Cheers, by the way. Hello, everyone, by the way. Hello. How are you guys doing? Alrighty. So, and what I want you to do today, right? So if we take a look at the circle that we generated, it's kind of a, it actually has like a, white background. So let's actually make it more neutral, right? So let's generate something like this. Flag GP. It's not a FP, it's a flag JP. There you go. And if I open it again, so this is a black flag of Japan. If you zoom in on this circle, you may notice something pretty meh. It's very like the pixels are not smooth, right? There is a stairs of pixels. And this is because this library doesn't have any anti-aliasing implemented for it, right? So, and this is going to be today's topic, right? So today I'm going to go ahead and try to implement anti-aliasing for this specific library. So when you render your primitives, they actually look smoother. They don't have these stairs and stuff like that. And if you Google up what is anti-aliasing, just render it in 2 times the resolution and then squish it to anti-alias thing. Well, you are actually really close to how anti-aliasing works, believe it or not, right? You basically described how anti-aliasing works, but essentially the idea is the following. So resizing, if we're going to resize things, we still have to do it ourselves. You have to keep in mind that the only thing we have at our disposal is put a pixel at coordinate XY. That's it. Right, we don't have any third-party dependencies. We don't use anything like Cairo or Cairo, I don't know how to pronounce this library, or anything like that. The only thing we have is please put this color at that position, like replace that pixel, and that is it. And with this ability, we have to implement lines, circles, rectangles, triangles. We have to implement literally everything. So we don't have an ability to resize thing. We can only place pixels. That's kind of the point, right? So if we want to just resize thing, we have to implement resize ourselves, right? So, and speaking of how anti-aliasing works, it actually works on a level of subpixels, right? On a level of subpixels. If we take a look at the pixels, right? So pixel is basically, you can treat pixel as a square, right? So that means your screen is a grid of squares, right? So let's take a look at the imaginary screen, right? So this is the imaginary screen. So, and every time when I need to draw a grid, it's usually a huge pain in the ass because I have to slowly do that like that. Right, so slowly and painfully drawing each and individual row. Anyway, so essentially, when I want to draw a circle, right, I start at a particular center. Then I figure out the radius, right? I usually know the radius. Let's say that the radius is going to be 3, right? So this is basically the radius. So essentially what I do, I actually step up the size of the radius, like so, and step left also with the size of the radius, right? And then on here on intersection of these two things, I find the left top corner of the square that sort of covers the entire circle, right? And then I actually outline that square and I iterate through each pixel of that square. And then I take coordinates of each of that pixel and see how close it is to the center. If it's closer than the radius, that means I have to color that pixel. And that way I actually render the circle. Okay, so this is how it works right now. The idea of subpixel rendering is the following. Imagine that instead of iterating each and individual pixel, we'll actually iterate subpixels. We divide our pixels into smaller chunks, right? So let's say that each of our pixel is actually 4 pixels, right? So, and instead of iterating each pixel, we actually iterate like small subpixels. Let's imagine that, for instance, we figured out that for this pixel, we have to color it. This pixel goes into the circle. Maybe this pixel goes into the circle, but these two don't go into the circle. What's going to be the final color of that pixel? Right, maybe it's going to be basically the percentage. Right, so essentially we see that 50% of subpixels actually fall into the circle and 50% of pixels don't. So for that one, we're gonna have the color of the circle with 50% of opacity. You see what I mean? Right, so essentially we kind of like emulate a higher resolution. Right, we don't have a higher resolution, but we emulate the higher resolution. So, and that's why I said that you were kind of close to like how anti-aliasing works, right? Just render it at high resolution and just resize it down. This is basically that. This is basically rendering it at high resolution, twice as high resolution, and then scaling it down. So you were kind of right. So that's how it works. Does anyone have any interview questions? I remember there was a really cool CMD trick for software anti-aliasing. Yeah, CMD actually falls really nice when it comes to doing rendering like that. I think at some point we're gonna do CMD, that's for sure. Do you pay for Copilot? I don't have money. I don't pay for anything. This is not on topic question either. Would you need to use floats for that? We can try to use floats, but then we can try to figure out how to do that without floats. Right, again, to do that without floats, we can essentially just render it in an imaginary higher resolution with integers, if that makes any sense. We'll see how it goes. So I'm gonna start with floats, and then I will try to figure out how to do the integers. Can we just like check just for a little bit bigger distance and then divide? Maybe that's basically what we can do. Yeah, sure. But again, it basically sounds like rendering it at higher resolution and just scaling it down, right? All right, so let's continue. Let me see how we're going to do all of that. So Olive.c circle, right? So this is where we start rendering the circle. First thing we do here, we just create a normalized rectangle. That makes sense. That's pretty cool. And now here we have the pixel X and Y at position X and Y. So for now, I suppose one of the things I want to do is maybe I'm just thinking. Organize some sort of a loop, right? So I need to iterate subpixels, right? I need to iterate subpixels. What's going to be the best way to iterate subpixels? All right, so maybe we're going to do something like SX, so it stands for subpixel, right? It's going to start at 0, SX2. So for now, the resolution of the anti-aliasing is going to be 2 by 2, right? So we're going to have 2 subpixels, just like I showed in the drawing, right? I don't know if it's the best way to do that. In fact, I don't really care if the things I do are the best way to do things. I just try to do things that work, right? And if something doesn't work, I try to improve upon that specific problem that doesn't work. Right, so here it is. So here it is. So this is the subpixel, and because of that, we want to move all of that code in here, right? So iterating the main pixels, then within the pixels we try to iterate subpixels. So let me actually maybe open my pane just so I can have something in front of me. So let me see some stuff. Right, so essentially I'm going to do the following thing, right? So this is SX and this is SY, right? 0, 1, 0, 1. So 0, 0 is going to be this subpixel, 1, 1 is going to be this subpixel, right? So to find the distance, we're probably going to have like a even padding between all of those things. So that means what we have to do, we have to take 1 and divide it by 3, and that is going to be basically the distance between these sort of like subpixels, right? So let's actually do something like so. Since it's basically constant, I think I'm going to put it in here. So float spad, right? So I'm going to divide 1 by 3, right? So this is going to be 1 by 3, which actually makes it sort of like customizable, if you know what I mean. Right, so we can maybe define some sort of a constant, right? So res, right? So this is going to be res, and res is basically the amount of subpixels in here. So here we have 2, so that means it's going to be 2. Because of that, the padding between them is going to be res plus 1. It's going to be always plus 1 because you have, even though you have 2 pixels in here, you have 1, 2, 3 spaces in here. That's why you have to always divide by it, like, you know, plus 1, right? You have to divide it plus 1. At least this is how I see that, right? And then here we can do a res. So having this constant actually allows us to customize, right? So we can actually keep increasing the resolution, right? So maybe I should also pre-calculate this entire thing, right? So let's define a pad, and I'm going to just like move this entire thing there. So this is going to be a pad. All right, that is cool. So that means now, where is the position of that subpixel, right? So the position of that subpixel is around a pad plus sx multiplied by a pad, right? So we always have this initial padding, right, for the top left corner, and then the amount of padding is basically the coordinate of that specific pixel, right? So this is how it's going to be. So this is for x, and then what we have to do, we have to add it to x, right? So we have to add it to x. So, and this is basically the actual subpixel. So this is more of a like subpixel offset. So it's going to be socks, right, and soy. Anyway, so we have socks and soy, which is a subpixel offset. That's what it stands for. It's a subpixel offset. Right, socks and soy. Soy socks. I mean, imagine like actually making a socks out of soy, right? Is there like enough like fiber material to make you know, clothing from soy? I'm pretty sure there should be something like that. Yeah, that's for sure. And this is an actual subpixel coordinate in here that we're gonna put like here. There you go. So this is gonna be y, and this is y, and this is another y. Interestingly enough, we can probably maybe move this padding outside and just like do it like this, plus 1 multiplied by that, right? And this one could be multiplication, and there we go. So this is basically what we have. Is that a good idea? I think it should be fine idea. So, and now, instead of using x and y, which is the coordinate of the pixel, we should use the coordinate of the subpixel, right? So we're finding the distance between the center and the subpixel. Interesting enough, the coordinate of the center is not particularly what you would think it is, right? So you have another pixel in here, and that pixel is the center, and the coordinate is actually this top left corner. So we're finding the distance between these things. What we have to find instead is probably the distance from the center of that center pixel, right? And because of that, I think what we have to do, we have to actually add half, right? So let me put something like this in here, then plus 0.5, there you go. So I think that's what we have to put in here, right? And of course, this entire thing should become float, right? So I would like to make it not float, I would like to keep it integer, right? But for now, I'm just figuring out how this entire thing would work, right? So I just want to have something working, and once I have something working, I can try to improve it and maybe make it, you know, completely integers, but I'm not sure how to do that for now. All right, so that should be basically it, right? So I don't think... So basically I took the pixel, I split the pixel. Okay, so there is one problem in here, right? So there is one problem. And the problem here is that we need to accumulate all these pixels, because here we can't just like set pixel. We have to figure out how many of them we need to set and how many of them we should not set. Interesting enough, so we can basically count, right? We basically can count how many subpixels fall into the circle and how many of them do not fall into the circle. So we're going to start with 0 in here, and when we know that a particular pixel falls into the circle, we just do plus 1. That's it. And then after this, we can take a count and divide it by AA resolution multiplied by AA resolution, right? So the amount of subpixels is basically resolution squared, right? And then we can take a percentage of how many of the pixels actually fall into the circle, right? The percentage of them, you know, in the single pixel. And we can use this percentage as the alpha for the color. Does that make sense? I think that's actually pretty cool. Yeah, so maybe we should be able to basically take the alpha out of here, but yeah, we'll have to do that at some point. So one thing I wanted to do, I wanted to actually get rid of this body. Right, so let's actually get rid of this body, and there we go. So this is basically what we're counting. Now I need to figure out the percentage in here. How are we going to be doing that? So the easiest way to figure out the percentage is just like convert both of these things to float, right? So I'm converting them to float. And essentially what I have in here is the alpha of that thing. So, okay, now I need to adjust my color to have the alpha, to have this specific alpha. Right, so maybe I can even just like convert it to uint preemptively, right? So to do that, I can multiply it by 255 and just force it to be uint32, right? There we go. And I force it to be uint32 because I'm going to be merging it with the original color. So the alpha is located in here, right? So this is the mask that sort of like removes the alpha. I might as well actually do something like this, 0, and the rest of these things is going to be alpha, right? So I take my color and I just do AND with it, effectively removing the whatever alpha it has in there, and then I can basically shove my alpha into that, right? So, but that creates some kind of a problem. The original alpha of the color is kind of lost. And maybe we should take it into account, if you know what I mean, right? So maybe we should take it into account, but I don't really want to think about it too much right now. So what I'm going to do, I'm going to basically put a to-do about that, right? So let's maybe uint32 updated color, right? So this is going to be updated color, and we're going to be actually blending the updated color in here. So I'm going to put a to-do. This effectively ignores the alpha of the original color. Maybe we should take it into account somehow, right? So we should take it into account somehow. I'm not really sure how exactly yet, and I don't really want to think about it too much right now, right? So I just want to have something working. So I think that is it, right? I think we should try to go ahead and just like compile the entire thing and see how it goes. All right, so what do we have? We have uninitialized stuff in here, so this has to be actually socks and soy, right? So this must be socks and soy. And everything seems to be compiling, right? So everything seems to be working, everything seems to be twerking. So let's actually try to compile the Japan flag, and let's take a look if we manage to generate a better Japan flag. And we couldn't generate a better Japan flag. We didn't generate anything at all, which is quite surprising, I gotta say. So let me try to set the color white. Let me try to set the color white and see. So the entire thing should be white, and there is no red color whatsoever, right? So there is no red color whatsoever, which is rather surprising. So what if I use the original color in here instead of updated one, right? So let's actually give it a try. So let me see. Yep. Why are you asking me questions, Emacs? Stop asking questions. Thank you. And we have... This is actually really funny. Well, I mean, I do understand why this happens, right? This is because we are iterating the square within which we are sort of carving the circle. So this is the new Japan flag, by the way. Did you know that? So this is how pixelated Japan flag looks like. So they basically censored the circle. This is actually a pretty good idea. A Japan flag, but with the circle pixelated, like censored. I wonder if anyone actually made that joke before. Somebody should make that joke. This is actually a pretty cool joke. Somebody should make it. Fuck. Okay. So let's see what is going on. What is going on? So this is the padding, and I just like take one, and the padding is actually divided by 3. So, and we find the distance from this thing to that thing, right? And then dx dy, and we just count this entire stuff. All right. So 2 by 2 has to be 4. So let me try to maybe actually reduce the size of the flag, right? So I'm just thinking about a better strategies to test all of that, right? So what the hell is that? Okay, that's weird. That's Emacs moment. Okay, so I'm gonna try to generate this thing, and now we should have a very small flag, but not really, right? So we also have to reduce this entire thing. So I basically divided everything by 10, right? So I divided everything by 10, and let me see, there we go. So we have now a very small flag. So the reason why I reduced the resolution of this entire thing is because I want to literally print the count for each individual pixel, right? I just want to see what's going on in there. Right, so do we even, like, what kind of counts do we even have there? And to reduce the amount of spam, I want to do this stuff. So flag Japan C, so let me include stdio, right? So I'm including stdio, and some of them are 2, some of them are 4, right? So, and yeah, if we take a look at the like rows, we can clearly see some sort of like yeah, that actually works nice. I'm pretty sure I can even do a pretty cool thing, right, where I split them by spaces. Right, I'm gonna literally split them by spaces and put a new line in here, effectively drawing it with ASCII. Right, and we even have a circle with anti-aliasing, but with digits. Okay, it's pretty fun. I really like that. Look at that shit. Yo. That's so cool. we can clearly see that, but it still doesn't really work properly when we divide everything. All right, so we can try to do this kind of thing. So let me see. I want to take a look at the alpha, right? So I'm going to do x alpha 0, 2, right? So let's actually take a look at the alpha, and it seems to be working. It seems to be working. So this is x and y, and when I'm updating color, I don't really know. So let me take a look at the updated color then. Updated color. So the color is supposed to have 8 of these things, right? So we're gonna have 8 of these things. So I need to... Do we even have anything? Oh, I'm an idiot. Of course. I should put the alpha into this byte. And to put the alpha into this byte, I have to move it 3 bytes to the right. Of course. Okay. I'm really glad that I decided to actually debug it like that, right? So because I can clearly see it in here. Okay, so let's actually recompile this entire thing, and it should work. I'm pretty sure it should work. So I'm gonna bring everything back, and I'm going to generate an actual image. Right, so let's take a look at the final thing, and this doesn't look like a final thing. What the fuck? Wait a second. Olive.c and updated color. There we go. So we're going to be using the updated color. Let me take a look at that, and look at that circle. Now I'm going to zoom in on that circle, but to actually make it easier for you guys, I'm going to put the background like this. Right, so we're gonna have like a grayish background, and let me open this thing. Let's take a look at the anti-aliasing. Look at that smooth edge. Holy shit! Yep, we implemented anti-aliasing, and it's basically rendering it in higher resolution, right? Because if you take a look at the implementation, what we effectively doing, we're just rendering it at twice as high resolution as it was, right? So we can even give it more resolution, right? So let's actually divide it 3 by 3. But the more resolution we give it, the slower this entire thing will become, right? So the slower it will become. Rogelio171, thank you so much for Twitch Prime. Thank you. Excited Crowflick, thank you so much for Twitch Prime. I'm sorry if I missed anyone. Thank you so much. Exiled Crowflick, I don't know. I'm sorry. Can you try skipping multi-sampling when it's not on the edge? Maybe, we'll see. So, I mean, it's too early to ask these questions right now. You're guys jumping to optimization really early. We just implemented something working. Don't try to optimize it yet. So that's the problem with people getting really discouraged early on. You're trying to make it like the most optimal solution right away. Just say fuck it, implement dumbest, slowest solution, but that actually works. That's what's important. So this is a very dumb solution, but it fucking works. It fucking works, and it's amazing. And let's actually iterate on that, something working. Don't rush it. Okay? So let me see. So let's actually see how slower it became. Right, as I already said, this is a very slow solution, and by the way, it should probably break the tests. Right, it must break the tests. So let's actually run some of the tests, and let's see. So it broke the fill circle test. Right, so it broke field circle test. So if I take a look at the actual thing that got generated, the actual thing does have anti-aliasing, right? And it actually blends with the circles behind, right? So as you can see, this blue blends with the red a little bit. All right, and if we take a look at the diff, right, so let's actually take a look at the diff. You can clearly see, so this is the difference between expected and actual, and the difference is at the edges of anti-aliasing. So this is precisely why I implemented this testing framework that can actually highlight the differences, because once you start implementing features like anti-aliasing, it becomes kind of important. You can see the actual difference between those things. Right, so yeah, that's actually pretty cool. All right. So I wonder what else can we implement in here. We can do similar thing for triangles. We can try to do similar things for triangles, but that's gonna be rather difficult. Maybe, I don't know. Let me actually think. Right, so for the triangles you have 3 points, and you consider those points to be essentially at the centers of the pixels, and then you do subpixeling. Yeah, so that should work actually. But for the triangle, I think, by the way, for the triangle you can probably try to do subpixel rendering only on the edges, right? And it's actually rather easy to do that. Should be rather easy to do that. Okay. So what I'm thinking is, how can we do all of that? How can we turn this into the integers, right? How can we turn it into the integers? It is rather interesting. So let me do it like this. Oh, and another thing that I want you to check, by the way, I want to check how the triangle example works now. Did it become slower? It actually doesn't work anymore. Yeah, so that's basically the problem with not taking into account the alpha, right? That's the problem with not taking into account the alpha, because this thing is supposed to be transparent, but it is actually not. So we have to actually go ahead and implement that. And I'm thinking, how are we going to implement that? I think we can use this alpha as basically the interpolator, like a linear interpolator from 0 to the original alpha, right? So yeah, why not? Let's actually keep it like that. I'm gonna keep it as the interpolator, right? So this is our interpolator. And then I want to extract the original alpha, right? So the original alpha, we do color FF000000, right, 1, 2, 3. So, and this is the alpha, and we want to shift this entire thing into 3 bytes, and this gives us the alpha, right? So this gives us the alpha. Nameless Blossom, thank you so much for Twitch Prime, thank you. Right, so this is alpha, and maybe I just want to multiply it by t, right? We can try to multiply it by t. And that way, I think that is it, right? So that should be it. So that will interpolate it from 0 to the original value, right? So, okay, let me try to do the Japan flag thingy, just to see how it works. Right, so the Japan flag still works, right? So I think it still works. And now let me rebuild everything in here, right? And run the triangle example. And now triangle example works. So, and let's take a look if it has anti-aliasing. Oh yeah, that's actually very cool. Right, so the circle itself is semi-transparent. It has the anti-aliasing at the edge, and you can clearly see that the triangle doesn't have anti-aliasing. And it's still rather fast. It's still quite fast, even though it uses like a floating point. I'm quite surprised. So that's pretty cool. So, and all of these things also should work in the browser, right? So let's actually check how it works in the browser. So we can compile all of that to WebAssembly, right? HTTP server 6969. All right. So we're serving this thing. And here is an example, right? So this is running in the browser. So this is the same example. And let's take a look at the thing in here. Well, I mean, okay. So we have an anti-aliasing that is done by the browser, apparently. So it's not really anti-aliasing. I suppose it's like a bilinear interpolation of some sort. But yeah. So, but it's kind of fine. Maybe the resolution of anti-aliasing should be kind of customizable, right? So let me try to do that. So since I want to make this parameter sort of like a public interface of the library, right? So I like to prefix it with the prefix Olive.c. And here, means we have to do this padding, and this is going to be a res. So maybe I should call it resolution, but it's too long. Okay. So the way I'm going to do that, right? So if this thing not defined, by default, I'm going to define it as 2. So that way, right, that way, if you don't want to have any anti-aliasing in your library, what you do, you can just define this thing to be 1, and that will effectively disable anti-aliasing. Right. So yeah, I think it's a pretty good way to customize this thing. What do you guys think? So this thing makes it actually, I don't know how to say, right? It makes it also part of the public interface, but it actually should be not a part of the public interface. So I think I'm gonna go ahead and move this thing like that. So the only place where we need that is here. So that means I probably want to do it like that. Let's call it pad. And it's going to be like this. And I'm going to hope that the compiler is going to basically optimize that out. Right, so it will see that you shouldn't really allocate this variable. I don't modify this variable anywhere, so I hope it will simply inline the value, the final value, like in here. So I'm going to hope for a little bit of the compiler optimizations. What happens when you put half in there? Well, you're gonna have some trouble, I suppose. And I mean, is that the fact that you can put half in there, is it something bad? I mean, you can dereference a null pointer, sure. I mean, you're programming in C. You're supposed to know what you're doing. All right, so let me see. Okay, so this one has to be that. There we go. So now this resolution is controllable, right? So you can specify like how much of the resolution, and I think I'm gonna put that thing at the top of this stuff. We already have like a very similar parameter, which is called Olive.c def, right? So, and essentially it's a macro that is put in front of each function definition. So, and by default, all of these functions are static and inlineable to encourage the compiler to inline them and optimize them out. Right, but if you want to compile this program to a library that exposes all of these functions, you would probably, before including this entire thing, you would just define Olive.c diff, which basically zeroes out all of these static inline definitions and exposes all of the functions, right? So basically, we have sort of like compile time parameters for the library that you can like customize stuff if you want to. The same goes for res. Okay. So circle, we go in here. I want to actually test how this entire thing works. So we're gonna do flag Japan. All right. So as you can see, something went wrong. So that means I didn't disable this thing, which is kind of weird, isn't it? Because, wait a second. Right, if you have one in here, right, if you have one, why when I set AA rest 1 in here, it doesn't work with the Japan flag? Why it doesn't work? It still has a little bit of anti-aliasing. It still has that. And that is extremely weird. That is extremely weird. Because this thing is equal to 1, right? It is equal to 1, everything is understandable. So that means you just like do one iteration in here. The padding, because it's +1 and you divide it by 2, the padding has to be 0.5, right? It becomes half. So this is the padding. Then here we always do +1, so you always add half, right? So you always add half. You always add half to here. And then you take the center, you take the difference from the center. So yeah, effectively what you do in here is just like this minus half, and if it's that, it's +1, right? Which does make sense, doesn't it? And since this thing multiplied by itself is going to be 1, this entire stuff is either going to be 0 or 1. It's either 0 or 1. And because of that, alpha is going to be either 0 or 255. There's nothing in between, right? Like, I don't see anything in between. So, which implies that there should be no anti-aliasing at all when I set with it. Okay. Fuck you. Okay, I suppose I forgot to refresh the image or something like that. I don't fucking know what happened, but... so, okay. God damn. That's why I hate programming. Imagine like, sort of like step by step, like mentally debug your program. Like go line by line, and reason each line. Prove to yourself that that line makes sense, and then it magically works because if I forgot to refresh some caches or whatever, yeah, of course. Freaking caches. Who invented caches? Why do we have caches? Let's just make super fast CPUs that we never have to cache shit, and also super fast internet. Should I blame caching.com? Wait, is that a thing? Wait a second. Just a sec. You're gonna show my... okay, that's fine. Advice may be invalid due to caching. Okay, so... thank you so much. Alright, let's continue. Let me see. And now, if I set the resolution to 2, it should automatically have anti-aliasing. Does it have automatically anti-aliasing? Yes, it does. Isn't that cool? Isn't that cool? I think it's pretty freaking cool. Yo. Okay. Olive.c. So maybe the time has come to commit, to do a committee, and maybe even push. So I'm still kind of thinking, how can I turn this into integer, right? How can I turn this into integer? I can try to save this thing, right? So that I can start working with this stuff. Let's inline sx and sy, right? So instead of sx, we're supposed to have this thing, right? So this is going to be sx. Boom. And instead of sy, we're going to have this thing. Cool. So what's interesting is that x, y, sox, soy, sx, and sy, they all are integers. The only non-integer things are padding and 0.5, right? So can we somehow just sort of like move those things away, right, and group the integer parts together somehow, right? You know what I mean? Another interesting thing, okay, we can sort of like multiply those things somehow by something to make them integers. Yeah, that's the strategy. That sounds like an interesting strategy. All right, so let me try to open some of the parentheses, right? So we're gonna start with that. So yeah, one of the trick we can have is to keep multiplying all of these things to something until they become integers, right? Until, for example, this thing become 1, if you know what I mean. So, all right, so that means I can open this stuff up. And let's open this thing as well. So this just becomes padding, and this just becomes pad multiplied by that. All right, so maybe for the padding, so for instance, like imagine that pad is integer. We can try to ignore pad, and we have only 0.5. How can we make this entire thing integer? We can multiply dx and dy by 2, making this entire thing 1. And then, to compare it with r, we would also have to multiply it by 2, right? So we'll have to multiply this by 2, and then multiply this thing by 2, just to make this thing like integer, right? So we're sort of bringing it to like a higher resolution, if that makes any sense. So this is basically the trick that I'm thinking to employ, if that makes any sense, right? So I'm thinking to employ that trick, but I just first need to group things so that makes sense, right? And another interesting thing is that because of that, the integers that we're going to be comparing, they're going to be pretty huge, and this is something that we'll have to keep in mind. This is something that we'll have to keep in mind. But if I just multiply this thing by 2, it's only going to get rid of these ones, but it's not going to help with pads, right? So because pads are actually like a fraction, right? So this thing is like a fraction. So what should you multiply padding by to turn this thing into integer, right? Right, because you divide this thing by that. So effectively, well, I mean, you have to multiply it by this thing. Well, yeah, effectively, you need to multiply it by that, by the resolution plus 1, and it will cancel out this entire thing. Okay, that is very cool. So let's try to do that. Let me actually put this thing to integer, right? So this is going to be res1, indicating that it's a res plus 1. So once you multiply it by res plus 1, what's going to happen? Right, so let's just multiply it by res plus 1. And because of that, we also have to do res 1, like so. This thing goes to here, so res 1, cool. By multiplying res 1 with pad, you cancel it out, so we remove this thing. By multiplying it with a pad again, you cancel it out as well. You would have to multiply this thing with the res 1, of course, and then you have a half of res 1, right? Res 1, there you go. And there you go, we got rid of that float part, we got rid of this pad. We never have to go back to it ever again. So, but we still have some fractional part in here. We can rather quite easily get rid of it by basically always saying that this thing has to be divisible by 2. But we can multiply this entire thing by 2 as well, right? So we can just do something like by 2 and multiply by 2, multiply by 2. Right, so once we multiply this entire thing by 2, we have that, then of course we have that, and then of course we have that, but then effectively we get rid of that, right? So, and now we can quite confidently say that these things are integers, can't we? I think we can. It's like basically logical reasoning of some sort. We can simplify some of these things. We can maybe move some like 2's here and there, but why? I don't think it makes sense to do that, right? So I don't really care about it too much. Okay. So, but we only simplified this thing, right? So we'll also have to do something in here, but we'll see. Okay. All right, let me see if it works. Flag GP, and I think it worked. Did it? Okay, so let me disable the anti-aliasing. All right, so I'm gonna put 1 in here. I'm gonna put the resolution, and then I'm gonna refresh this entire thing, and it freaking works. Holy shit, I didn't expect that it would work. Yeah, I think I came up with a general approach on how to take like a floating point graphics code and turn it into integer. So, and effectively what we did in here, we increased the resolution, right? We just do all of the math in a higher resolution. This is so cool. Well, and of course, some of the integers in here can overflow, right? This is something to keep in mind. Maybe because of that, we want to use like 64-bit integers and whatnot. But I mean, here's an interesting thing. If you have like a full HD, right? So it's a 2K, right? 2K. You use AARes equal to 2. You have 2 millions. 2 millions fit perfectly into 32-bit integer, right? So you can do anti-aliasing at like full HD. If we need something bigger, we can just do 64 bits. And 64 bits, in fact, can even like can accommodate even higher resolutions, like magnitudes higher, right? Because we're talking about exponential stuff. So yeah, I think we'll have to switch to 64 bits in here. Switch to 64 bits to make the overflow less likely. And also research the possibility, the probability of overflow, right? So how likely and what are the conditions in which this entire thing will overflow and fail miserably, right? So the cool thing about floating points is that like it has a scaling precision, right? So you don't have to think about too much. And even floating point can fail miserably, right? So if you spend too much of the precision. Right, so, but with integers, right, it's just faster and more precise, I would say, right? With floating points, you have to always like think about the errors that the floating points may produce and blah, 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 you know, usual stuff. Okay, so now we still have floating point parts in here, right? Still have a little bit of floating point parts. How can we get rid of them? The usual trick. So we have a floating point t. Let's inline this entire thing to here. Right. And here is an interesting thing. So we can just keep it like that. Yeah, we can keep it like that. Because the first thing we do, right, we just multiply those things together. Right. And then once we're ready to ignore the fractional part, we just perform the division. Interestingly, yeah, so we can actually do something like that to make it more readable. There we go. That should work, I think. Yeah, that should work. So now we implemented anti-aliasing entirely with floats. That is actually so cool. So, you know what's also cool? Is that maybe we can even merge these two loops together. But I don't think it's worth it. So, because I'm pretty sure the compiler is going to basically unroll this entire thing because this size is known in compile time. In fact, a lot of these things with these loops are known at compile time, so I would expect to compiler do like go batshit on this thing and just reorganize however it wants. Like I'm pretty sure these loops are not going to exist in the final execution. Right. Okay, but the problem here is that this kind of obscures the logic of the anti-aliasing. Because, for example, I only use like this very specific strategy of dividing the pixel into subpixels. What if I want to divide them somehow differently? How am I supposed to modify this code? I don't know, I'll have to start over, right? I'll have to reinvent a different way of dividing by subpixels. Right, so for instance, what if I want to divide them by 3, right? For instance, like so, right, in a triangle. It's a completely different code in floating points. So essentially, I just obscured the code, right? It's a more obscure code. It would be kind of cool if we had a compiler where I would just do things in floating point and turn it into integers. But maybe Clang is already capable of doing that, who knows? Because Clang is insanely smart, right? So it can replace your loops with memsets and stuff like that without realizing that you're not linking with a standard library that doesn't have any memset. It's extremely smart. So maybe it can do stuff like that as well. Who knows? Who knows? Who knows? Alright, so let me just double check that this entire thing works, right? So we have a simple resolution in here. Is that a caching yet again? Man, what the fuck? I feel like it's a cache. Okay, so I'm not gonna use Emacs anymore. I'm gonna just do B black. And yeah, use the buffer. Yes. I'm gonna also disable anti-aliasing. And now I'm going to go to here and just do 2. And I'm gonna refresh this entire thing, and now we have anti-aliasing, which is poggers. Okay, I think the time has come to do this stuff. I want to update my tests, right? So because the tests are extremely important. So we already know that the tests with the fill circle don't work because of the anti-aliasing, which is totally fine. So let's take a look at what else doesn't work. So alpha blending doesn't work as well. Let me take a look at what doesn't work. Alright, so we have this kind of thing, and I want to take a look at this thing. Okay, so it doesn't work for the same reason. Right, it doesn't work with this thing. I'm gonna go ahead and just say, all right, update the tests. I'm gonna do record, right, and it actually updated all of them. So now, if I take a look at the circle expected, what it expects, it also expects anti-aliasing. And you know what's cool? Since anti-aliasing, like our implementation of anti-aliasing is completely in integers, it is more predictable. Right, it doesn't use any floats, so it's gonna be fine. People saying I have some sort of a bug, but I'm not sure how to see that bug. Right, so what kind of bug do I have in here? Because I don't understand this code that I came up with. Right. What I can see is that the anti-aliasing works. Oh, +1. Oh, okay. Yeah, I remember what you said. Okay, I see. Thank you so much. Yes, yes, yes. It has to be +1. Yeah, you're right. Now I can see that. So the problem with this code again is that the logic behind that code with floats is completely obscure, and if there is back with that logic, I cannot fix it in this form. +2. Why +2 exactly? Where is the other 2 comes from? I don't understand. Where is another one? And multiply. Ah, okay, I see. All right. Yeah, you're right. You're right. You're right. Thank you so much. Yes. You all are correct. Okay, so let's actually see. What if I try to run the test? Test still pass. That's what's funny. I mean, I didn't recompile this thing, but yeah. Let's actually see the tests. Test still pass. Damn. I guess it worked. So that's kind of funny. Yeah. It still worked correctly. Everything works accidentally, right? Everything works accidentally. What's interesting is that maybe we can even use the same code. For instance, for the for triangles, right? Yeah. So to reuse this code, I need to somehow abstract it away. It worked because of the high resolution. The +1 doesn't make change. Yeah, I see what you mean. But yeah, thank you so much. Anyway, okay. So let me now see if the triangle works, right? So I probably want to have some sort of way to do benchmarking to see how it affects the performance and stuff. Right, so here we do have anti-aliasing, and for the triangle we don't have it. Okay, so let's do a committee and maybe even pusher. How about that? How about that? Implement AA for circles. There we go. And I'm gonna push that right into the repo. Isn't that amazing, chat? I think it's goddamn amazing, bro. It's just bruv sounds like a dog barking. Bruv. Sorry. Anyway, cool. So if I'm doing the triangle thingy, right? If I'm doing the triangle thingy, how I'm gonna approach that? I feel like with the triangle, it's gonna be kind of difficult to approach that, probably. But yeah. Because, what do we do with the triangles? So let's have a grid. What the hell is that? Cool. Booba. This is the most painful thing. Alright, so we have 3 points usually, right? Booba. So we have 3 points, and we basically, like, logically divide this triangle into 2 triangles, right? And then what do? We just fill in, like, we scan the lines, right? We essentially scan the lines and fill them up like that. And the question is, how are we going to be approaching that, right? So here we start at the center, and then for this thing we have like 4 subpixels. Let's imagine that we have like 4 subpixels. How am I supposed to fill them in? Right, how am I supposed to fill them in? I know for a fact... So the only way I can fill that stuff in is by the triangles are a little bit more tricky. The triangles are definitely more tricky. So you essentially have to, you have to convert everything to floats again, and then then rethink, basically reconvert it to integers. So you need to start with like centers of the pixels in here, and then start with the sub-pixels of each individual pixel, right? And that's actually like, it basically have to go through the same process as with the circles, right? I can't just go ahead and reuse what I have in a circle, but maybe I can. Maybe I can reuse whatever I have in the circles, is because like I don't have enough information to do that. So I have to go through the same process again to discover the similarities between the anti-aliasing of circle and the triangle, and then I can see what can be reused. So right now it's not obvious how this entire thing can be reused. You know what I mean? You know what I mean? I think you do know what I mean, right? I think you in fact do know. All right, so, but maybe, I'm not sure if I'll have enough time to do that. That's the problem, right? So I'm not really sure if I'll have enough time, because I have like 40 minutes left for this entire thing. And will I have 40 minutes to do that? I'm not sure. Okay, so let's go ahead and try to do that. Where is my Olive.c? Olive.c. Olive.c. So essentially, what we have to do, we have to turn all of these things into floats, right? X1 has to be float, and its position has to be, yeah, let's put it like this. Float. X1 plus half. So we have to add half to all of them. Y1 is half, and the rest of the stuff is like this. So we're starting at the center of them, right? We're starting at the center of them. I'm just a little bit afraid that I'm gonna go into like a very deep rabbit hole if I try to implement anti-aliasing for triangles. So I think I'm not gonna do that. I think we're gonna try to do something different, right? So, right, we started with the anti-aliasing for the circles, and I'm going to implement anti-aliasing for the rest of the things already off screen. So I'm going to use the same process that I demonstrated in here, like first implementing it in flows and then convert it into integers. So I don't think I'm going to show anything new in here, but if I start to do that, I probably go over time. So yeah, I don't think it's a particularly good idea to do it like that. New to software development, do the best programmers need to be strong with math? I'm an idiot. So math is a very broad topic, actually. So to be good at math means actually nothing. It doesn't mean anything. Math is such a huge topic that being good at math, like, it's a meaningless sentence. It's just like saying I'm good at sport. What do you mean? Do you play chess? What exactly do you mean? Like, what does it mean to be good at sport? Which one? Right. So it's a very broad topic, right? So what do you mean? So I think the problem is that the modern education actually trained people to think that math is a very concrete and specific small thing, right? It's just like an annoying small little thing. It's like a small little pain in your ass. That's what the modern education trained you to think. And math is not that. It's a very huge like topic. Like there's even like different subcategories of math that almost do not overlap with each other. And the person who specializes on one thing, like, they will completely not understand what's going on the other side of math. Right. So what I would suggest you to do is to actually rethink what is math. Right. What I would suggest you to do is just realize that math is not what you think it is. Right. It is not that small little pain in the ass where you're forced to learn obscure rules to solve obscure puzzles. Math is not that. This is what you were taught in school and university or whatever you went to, and it's not math. You don't need to be good at that, that's for sure. You don't need to be good at memorizing pointless rules to solve pointless puzzles. You don't need to be good at that. I'll assure you.